what's the mass spec do? And I made the comment that we're going to weigh the molecule. Now, you realize there's no way to weigh a molecule. I mean, we're not even close to the technology to weigh a molecule, but we can get at the molecule's molecular weight indirectly by putting a charge on that molecule. So this is a sort of the diagram of the mass spec hardware. We're going to start with the where it says sample inlet. That's the effluent of the GC column, and then we're going to go through and look at the ion formation. We're going to look at the quadrupole. We're going to look at the detector. But let me take this apart for you, and let me start with what I'll call an overly simplified mass spec. And with this, I think I can get you to understand how mass spec works. And then more importantly, I'm going to add some layers onto it, and I'm going to get you to a modern quadrupole mass spec. So bear with me a little bit, and we're going to start off with a really simple concept of a mass spectrometer, and that is, this is a column, and those are the molecules coming off your GC. So as the molecules are coming off, we want to identify the molecule. How are we going to identify it? We're going to get its molecular weight. So instead of saying, hey, something's coming off the column, comes off around benzene retention time, I would say something's coming off around benzene and it has the same molecular weight 78 as benzene and the same fragmentation pattern, therefore we're sure it's benzene. So that's what we want to bring to the table. So as the molecules are coming off the GC, we need to weigh them, but remember I said we can't weigh them directly, so we're going to put a charge on them. We're just going to blast them with electrons. I call this an electron gun. It's called EI for electron ionization, and it's really just a filament. But what we're going to do is we're going to shoot very high energy electrons at your molecule. And if we hit your molecule, it's going to become positively charged. Now, I got to tell you, that's the first thing that confused me about mass spec, because I know a little bit about electrons, and they're negatively charged. So if I hit your molecule with an electron, shouldn't it become negative? And the answer is nope, it becomes positive. Why is that? Well, remember your molecule is mostly empty space. 99.9% just empty space. It's really mostly just a cloud of electrons just whizzing around. So if I have a high energy electron and it shoots through your cloud, your own electron will get repelled, will get kicked out, and you're left one electron shy, which means you have a +1 charge. So everything in GC mass spec takes on a +1 charge, or I should put it this way. If it's going to take a charge, it's going to be a +1 charge in GC mass spec. We do not get multiple charges. In LC mass spec, we do. In fact, we need to. If you want to weigh 100,000 molecular weight protein, we can't weigh that. We need to put 100 charges on it to get it down to 1,001 mass to charge ratio. So in GC mass spec, if it gets hit, it becomes positively charged, and as soon as that happens, it gets kicked out because we have something called the repeller electrode. So the repeller electrode is positively charged, and as soon as that molecule takes on a positive charge, it gets kicked out of the cannon. It gets kicked out of the of our source here, and we're going to shoot it across the mass spec, and we're going to try and hit the target on the other end. Now that target represents the detector. So on the front of the mass spec, I have the ionization. The back of the mass spec, I have the detector. So I'm going to take this ion, and I'm going to shoot it across the detector. I'm going to throw it as hard as I can, but no matter how hard you throw that, it's going to have a certain trajectory. So think about if I throw a baseball as hard as I can, gravity is going to pull it down to the surface. So this is what's going to happen if I shoot this ion across the mass spec. It is going to fall down and miss the target. So how can I then use this to weigh the molecule? Well, let's put an electrode in there, or a magnet. We'll put it down there at the bottom, and we're going to make it positively charged, or north pole of the magnet. And we're going to set it to whatever the exact force that gravity is pulling down, we're going to push up. So imagine this molecule, this blue trace here. Let's say that molecule weighs exactly 100 molecular weight. So gravity is pulling down with the force of 100. So let's turn on that electrode, and let's tell the electrode to push up with the force of 100. If we do that, that molecule will then push all the way through the mass spec. It won't fall, it won't rise, it'll hit the detector. So the detector's been hit, he knows he's been hit, he has no idea what hit him. So the detector asks the electrode, what voltage are you set at right now? And the electrode said, I'm set for 100 molecular weight. So the detector says, ooh, I just got hit by something, it must weigh 100, so I'll make a little tally, and I'll call that thing 100. So what if something weighs 99? Well, you can imagine if 99 came through here, it would be deflected too high up. It would miss the target. What if something weighs 101? Well, it'll be deflected too far down. It'll miss the target. So the only mass that could hit the target right now at this instant in time must weigh exactly 100. Does that make sense, right? So you've played with magnets before, magnetic levitation, right? Two north poles of magnets will repel each other. So what we're doing is we're pushing up with energy, and we're seeing how much energy it takes to keep the molecule from falling. So the trick is this voltage, this electrode changes from 100 to 101, 102, 103, 104, and it scans from 0 to 1,000 all day long. 0 to 1,000, 0 to 1,000, and if it ever gets hit, the detector says, hey, I just got hit. What molecular weight were you just set at? So that's how we're going to weigh a molecule. We're just going to scan all day long, and if it ever gets hit, we're going to mark down what hit it. So as crazy as this sounds, first of all, that's how mass spec works. And also, if you ever look at a modern balance, look at your Mettler balance, your Sartorius balance, your analytical balance works the same way. If you put a weight on it, or you put a sample on it, and the pan sinks down, and then inside there's an electromagnet, it turns on, and it pushes the pan back up until it reaches 0. And it measures how much current it needed to put into the electromagnet to push the pan back up. So as crazy as it sounds, this is actually how we weigh things in a modern world. So now I just described what's called a magnetic sector instrument, and it's a poor version of magnetic sector. I'll admit that. But I start with this because to me this is somewhat understandable. You played with magnets before. You know, magnets will repel each other. So that's what we're doing here. We're seeing how much energy it takes to repel the molecule. So so once I have this, I can now add another layer to get us to quadrupole. So I just described magnetic sector. That's the $1 million mass spec, and there's not very many of them out there. You don't really need one of those. But quadrupole is by far the dominant type of mass spec in the world. So instead of one electrode down the bottom, I'm going to have 4 poles or 4 electrodes, hence the term quadrupole. So I've got one electrode down below the sample. I've got one up there above it. I've got one in front, one behind, and if I were to turn this on its side, it would look like this. We'd be looking down those 4 rods. And on these 4 rods, I'm going to put a DC voltage. I'm going to pulse that DC voltage, and on top of that, I'm going to overlay a radio frequency. That's right about where you lose me in mass spectrometry. It's like radio frequency affects our molecules, but yes, it does. So imagine this. I'm a 100 molecular weight molecule. I just got hit by the electron gun. I picked up a +1 charge. I just got kicked out of the cannon. And now I'm moving across this room. And on the other side of the room would be the detector. So as I'm walking through here, there's a pole above, below, to the right, to the left. And the pole above me turns on. I'm positively charged. It's negatively charged. And I have forward momentum, but now I start to move up. And then the right rod turns on. So I move to the right. And then the bottom, left, top, right, bottom, left, top, right. And if I have just the right molecular weight, I will have a corkscrew trajectory that's stable enough to make it all the way through those quadrupoles, boom, hit the detector. So when the detector is hit, it asks the quadrupoles, hey, what molecular weight you were just set at? And it tells us what molecular weight was. So essentially it puts a spin on the molecule, and at a certain molecular weight, only one molecular weight at a time will be stable. So we often call this a mass filter, because that's what it does. We create all the masses up front at the very beginning in the source, but this filter says no one gets through unless you weigh exactly molecular weight of 2, and then no one unless you weigh 3, and no one unless you're 4, 5, 6. It goes all the way up. So when something gets hit, it just looks to see what number it was at. So the fact that it's scanning so fast, it appears to us as if this is instantaneous. When we see a mass spectrum appear, we see all the masses. We're really measuring them 1 to 1,000, 1 to 1,000, but put this in perspective. The fastest mass specs out there are now scanning at 40,000 AMU per second. So they can go 0 to 1,000 AMU 40 times in 1 second. So this is a very fast scan. It appears simultaneous to us. So if I do this right, and we have just the right molecular weight, one thing will be stable, nothing else will be stable, so it'll less one mass through at a time because it has that corkscrew trajectory.